Vectors are the main objects of study in linear algebra. They are the players on the stage of the subject. So we really ought to make it our job to understand what vectors are and what really makes them tick. A lot of the conceptual story about the ideas of linear algebra is about taking what we think we know vectors are, which is a very sort of narrow understanding in the beginning, and trying to broaden it out. And the key to the subject is understanding how to see the structure that makes vectors vectors, not just in the limited cases that we're familiar with already, but in new situations where we might not have thought that linear algebra even applies, as long as the objects of study in those situations have the same rules that govern them as vectors do, then we can use all the tools of linear algebra to study that environment as well. So in the beginning, we think about linear algebra as a process of solving a collection of simultaneous equations for several unknown quantities. That's where the story began for us. This is the taste of linear algebra that you often get even in a high school algebra class, right? Solve this simultaneous system of equations, find the values of its several variables separately, and then put a box around your answer and move on. But we need to do better than that if we want to get to a conceptual understanding of what linear algebra is really about. So the next step after that is that we want to begin to think about those several quantities, x, y, and z, or x1, x2, x3, x4, whatever. We want to be able to think of those several quantities as a single entity, package them together into a new kind of object that we're going to call a vector. So the next step in our evolution is to think about a vector as being a list of the several quantities that we're trying to solve for. That's going to be step one. That way we're not thinking about a linear system of equations as a bunch of separate equations and the unknowns as a bunch of separate unknowns. We're going to be able to think of a linear system of equations as really a single equation, and the unknown that we're solving for is a single thing, a vector, even though that single thing can contain multitudes, right? It contains the entries inside of it, which may be multiple. And in that viewpoint, we then are thinking of a vector as something which can contain a collection of capital N, when that capital N is either 2, 3, 4, 10, 17, however many unknowns that we have that we're trying to solve for, that's how many entries are in that vector. So we think in that viewpoint of a vector as being an element of an n-dimensional Euclidean space. So we can think of a vector with two components in it, for example, as a point in the two-dimensional xy plane. We can think of a vector with three components in it as a point in three-dimensional xyz space, an element of R3. We could think of a vector with 12 components in it as a point in 12-dimensional space, or an element of R12. And so that gives us a little bit more of a sense of what vectors are. They're just elements inside some set, and that set is defined in a particular fashion. But where we ultimately want to get this semester is we want to understand what it is that really makes vectors tick so that we can spot them not just when they're points inside of a Euclidean space, but when they're functions inside of a space of functions, or where they're images inside of an image gallery that we're trying to do facial recognition on. We want to be able to spot vectors in a whole variety of different contexts. And because anytime there's a vector, there is linear algebra. If we can spot vectors in a new context, that means that we can use linear algebra in that new context to understand how those vectors work. And so the real step of our evolution we're trying to get to this semester is to think about what makes vectors vectors so that we can spot them anywhere. And the answer to that question is what we're going to begin to talk about in this video, that what vectors are they anything for which the operation called linear combination can be defined. The last step in our evolution is to understand that wherever there is linear combination, there is linear algebra. Because wherever there is linear combination, there are vectors. So in this video, we want to take a look at the operation that we call linear combination. What does it look like? Where does it come from? What's some of the vocabulary that surrounds it? We're going to ground ourselves in familiar examples of vectors for now, but focus now on the ideas. Focus on linear combination as the single primary operation of study that makes linear algebra, and that makes vectors, vectors. To begin the story, linear combination is, at its basic root, just a combination, as it says, of two familiar operations that we can apply to vectors. The first is addition. We know that given two vectors, we can add those two vectors together and get a third. Thinking for the moment of vectors as being, say, points in the xy plane, for example. We can add vectors together and get new vectors. And so one component of linear combination is addition. The other is scalar multiplication. Scalar multiplication refers to multiplication of a vector by a single number, a scalar, which in our course, scalars are almost always just real numbers. But you can do linear algebra where that field of scalars are the complex numbers, or the rational numbers, or even finite fields. You can get all kinds of fancy other abstract algebraic stuff and bring it in here. For our purposes, scalar is just going to mean a single, usually real, number. And that's all that linear combination is. It's combinations of multiplying vectors by scalars and adding their results together. You'll recall that when we first were talking this semester about what makes an equation or a system of equations linear in the first place, remember what it was that we could do to the variables in those equations. We could multiply those variables by numbers, and we could add the results together, and that's it. Addition and scalar multiplication. Anything fancier than that, and we're not talking about linear equations, we're not talking about linear algebra anymore. So what makes linear algebra kind of nice is that these are the only two operations of arithmetic that are really on the table when it comes to working with vector quantities. Addition, scalar multiplication, end of story. So what we want to do now is look at some examples of what linear combination is and how it fits into our story of linear algebra so far. So suppose that I have these two vectors inside of two-dimensional space. I'm going to call this one v1, -2, 1, and this one v2, 3, 2. So you can think of those as the points, -2, 1, and 3, 2, inside of the xy plane. You should also get into the habit of when you write down a vector-valued quantity as a variable name, make some notation to note that it's actually a vector quantity and not a scalar quantity. So when I'm writing on the screen or on the board, I'll usually put a little arrow on top of a vector quantity like this one, just to remind myself that that quantity is a vector. If I don't put a little arrow on top of a letter, a variable name, that usually means that it's a scalar. When you read a textbook, very often in a textbook, vectors will be typeset as boldface. Sometimes they'll have the arrow over them, sometimes not, but usually they'll appear in bold, so you can differentiate the vectors from the scalars. So for example, if these are my two vectors v1 and v2, then how do I form a linear combination of v1 and v2? Well, the idea is that I can just take some scalars and multiply those vectors by those scalars. So let's say I take the scalar -1 and the scalar 3, and I multiply -1 by my first vector, multiply 3 by my second vector. So those are scalar multiplications of the vectors v1 and v2. And then if I just add those two together, then this whole result here is called a linear combination. -1 of the first vector plus 3 of the second vector. And from an arithmetic standpoint, I can finish that arithmetic just by multiplying component-wise. So this is how scalar multiplication works. If I multiply -1 by my first vector, that means multiply -1 by each of the components in that vector. If I'm multiplying my second vector by 3, that means multiply 3 times each of the components in that vector. And then when I add vectors, I add them component-wise as well. So when I add these two together, I'm going to get -1 times -2 plus 3 times 3. That's going to give me 2 plus 9, or 11. Same thing for the second component, -1 times 1 plus 3 times 2. That's going to give me 5. So what we would say is that the vector 11, 5 in this example is a linear combination of the vector -2, 1 and the vector 3, 2. Why? Because that's exactly how we constructed this vector. We constructed it by multiplying v1 and v2 by some scalars and adding the results together. And when I do that, I get 11, 5. Now, from a terminology standpoint, when we say the word linear combination, we're talking about this whole thing, this whole combination of addition and scalar multiplication of those two vectors. So linear combination means -1 v1 plus 3 v2. That's an example of a linear combination of v1 and v2. If we want to put the focus just on the scalars in my linear combination, and we often will, those scalars are sometimes called the weights in the linear combination. So it's a bit like a linear combination is a recipe out of a cookbook, and v1 and v2 are my sort of boxes of ingredients. And in my recipe, I have to figure out how much of each ingredient to put into my mixture. So the weights are kind of telling me how much of v1 that I want in my mix, how much of v2 do I want in my mix. So the weights are -1, so that's how many v1s I'm putting in, and 3, that's how many v2s that I'm putting in. So let's get a picture what does this actually look like? Because these are vectors in the xy plane. We have the xy plane as a visual that we're accustomed to. So let's take a look at a mental model for what this can look like graphically. So on this graph grid, what I've graphed are the vector v1, negative 2, 1, so that's this point right here, and I've drawn an arrow originating at the origin and going out to v1. Also the vector v2, 3, 2, so I've drawn an arrow for v2 originating at the origin and going out to the point 3, 2. So I can think of this v1 and this v2 as being visualizations of my vector. Now what's happening when I take scalar multiples of those vectors? Let's say I take v1 and I multiply it by, I don't know, 2. When I multiply a vector by a scalar, what it looks like in my mental picture that's in my brain for scalar multiplication is it's really just sort of stretching the length of that vector without changing the direction of that vector. So if I were to multiply v1 by 2, the result that I would get is a vector which is in the same direction as v1, but which is twice as long as v1. Similarly, if I were to multiply v1 by a negative scalar, take a look at what that does. That stretches my vector, but it stretches it in the opposite, exactly the opposite direction as the original vector went. So negative 3 times v1, for example, would be a vector which is 3 times as long as v1, but it points exactly in the opposite direction as v1 does. So as I vary the weight that I put on v1, I'm just varying the length of that piece of v1 that I'm going to put into my linear combination. And similarly with v2. If I multiply v2 by scalars, I get a bunch of vectors which are either exactly parallel to or exactly anti-parallel to v2. So when we created our linear combination to get 11, 5, remember that we picked some weights. I just picked these out of a hat, the weight negative 1 on v1 and 3 on v2. So let's take a look at what that looks like in our picture. So remember, in my linear combination, two things happen: scalar multiplication followed by addition. So first I'll do the scalar multiplication. That gets me negative 1 copies of my v1 into my recipe, as well as 3 copies of v2 into my recipe. And now take a look at what's happened. Here's negative 1 copies of my first vector, here's 3 copies of my second vector. And when I add those two things together, this is what addition looks like in the xy plane, if we want a mental model for how to add two vectors. When I add two vectors, what I'm really doing is I'm placing one of them at the tail of the other. So when I add v1 and v2 together, let me change the weights here for a second just to illustrate. Let's say I just have my weights as 1s. So 1 of the first vector and 1 of the second vector added together. That the result of that addition is that I'm placing the tail of one vector at the head of the other one. So v1 plus v2 is what I get by going out to v1 and then placing a copy of v2 there and going in that direction. You can see that what we get when I add two vectors v1 and v2 is we get a parallelogram whose diagonal gives me the vector v1 plus v2. Sometimes this is called a resultant vector, particularly if you're taking a class in something like physics. So to add vectors, we place the tail of one at the head of the other and get a parallelogram. This is called the parallelogram law of vector addition. So sure enough, when I take negative 1 of my first vector and I take 3 of my second vector and I add them together, that the result is a point that's just a little bit off of my graph screen here, unfortunately, but it does look to be the point 11, 5. So taking linear combinations of vectors is really just about finding multiples and then parallelograms, in a sense, right? That we're multiplying our vectors by scalars, we're adding the results together, and so anything that we can get out of that process is something that we will call a linear combination of my two vectors. So if v1 and v2 are the vectors I've sketched here in black here, then all of the purple vectors that I'm getting in this process are all different linear combinations of those v1 and those v2. And so a valid question for us to ask, and this is where we're going to pick up in our next video, is let's suppose we're asking the opposite question. Suppose that I have a vector like negative 2, 8, and I want to know, is that vector a linear combination of my v1 and v2? So we're asking the opposite. Not what is a linear combination, but is this thing a linear combination of our two known vectors? And that's where the questions really start to get interesting.